Hello everyone, in this video, we'd like to introduce our paper Social-NCE, Contrastive Learning of Socially Aware Motion Representations. Anticipating the motion behaviors of others is an essential ability in the social context. This ability allows us to not only keep a comfortable distance from the others, but also identify potential dangers ahead of time in complex scenarios, like the dense traffic shown in this video. However, building machines capable of doing so is not easy. The main difficulty arises from the complex spatial-temporal interactions among multiple agents. Oftentimes, these interactions are very hard to describe by handcrafted mathematical models. In the past few years, researchers have proposed a variety of neural network models to learn socially aware motion representations from data. Examples include RNN or transformers for sequence modeling, and pooling or attention mechanisms for spatial interactions. The learned model usually works pretty well in single-step predictions on the holdout test set. However, their robustness in the long-range closed-loop operation remains an open issue. In fact, even the state-of-the-art models still output unacceptable solutions, like collisions, from time to time, which raises significant safety concerns for real-world deployment. Why is it difficult to learn a robust motion representation? The key challenge stems from two sources. Number 1. Sequential prediction is not an IID problem. As illustrated in this figure, while the training trajectory in blue and the test trajectory in red start from the same state, these two trajectories may gradually diverge due to the prediction errors accumulated over time. That is to say, the state distribution is not fixed, but rather dependent on the learned model. Number 2. Training data is often severely imbalanced and lacks near-accident examples. Consider human motion forecasting as an example. Existing real-world datasets usually come from natural observations, where pedestrians may constantly stay in the safe regime, as shown on the right side of the figure, and rarely enter dangerous regions, measured by the separation distance between agents. The combination of these two sources poses a significant challenge. The sequential model is trained in safe spaces but tested in more dangerous scenarios. It's known that conventional machine learning models are not good at out-of-distribution generalization. Given such an ill-distributed training dataset, how can we learn a robust model for closed-loop sequential prediction? In this work, we aim to address this challenge by promoting robust motion representations through self-supervision. Our key idea is to explicitly model negative examples based on our prior knowledge. Intuitively, one effective way to explain the social norms behind the positive examples is to portray the opposite negative examples like collisions. We formulate this intuition into a new learning framework in the multi-agent context. It consists of two components, namely an auxiliary social contrastive loss, combined with negative data augmentation. Now let's first have a close look at the social contrastive loss through an example in the forecasting context. Most of the recent forecasting models are built with encoder-decoder-based neural networks, where the encoder extracts a representation of the historical observations from time 1 up to time t with respect to the agent I, and then the decoder rolls out the future trajectory recursively. The model is typically trained with a task loss, such as mean-squared error or negative log likelihood. In order to promote robust representation HTI, we introduce an auxiliary loss, which regularizes the feature vector such that it contains sufficient information for distinguishing a positive event from a set of negative ones. Here, the event is defined as the state S of the agent I at a specific time step in the future, for instance, time t plus delta t. We formulate this objective as learning an embedding space, where the projected feature vector of the history is pulled closer to the embedding of the positive future events while pushing apart from the negative ones. One crucial component of our method is the design of positive and negative events. Recent contrastive methods in vision and language domains often rely on carefully designed data augmentation for positive pairs while using random samples to form negative pairs. While this design choice is highly effective for unsupervised pre-training, it is not suitable for motion problems, since it does not bring more information and the main task about social norms. To more explicitly fill up the shortage of dangerous scenarios in the training data, we propose to draw negative samples from the neighborhoods of the other agents in the future, given that one location is rarely occupied by multiple agents at the same time. Our method can be viewed as a form of negative data augmentation that intentionally informs the model about low-density states through self-supervision, as opposed to laboriously collecting additional state action pairs from dangerous scenarios. We validate this method on a variety of tasks in the multi-agent context, including human trajectory forecasting and robot navigation in crowded spaces. On the forecasting task, we evaluate our method on 2 popular benchmarks with 4 different baseline models. The results show that our method can significantly reduce the collision rate by a clear margin, without degrading the prediction accuracy and diversity. Here are some qualitative results. Compared with the vanilla baseline, our method jointly adjusts the trajectories of multiple agents and outputs more plausible solutions. We further validate our method applied to imitation learning for robot navigation in crowds. The conventional behavioral cloning method suffers from a significant performance drop when the training data is limited. In comparison, our method is able to retain much better results, particularly in the low data regime, thanks to the additional information absorbed from the auxiliary contrastive task. We finally validate our method on Rainbow DQN, a state-of-the-art reinforcement learning algorithm. Compared with the vanilla and random sampling counterparts, the agent trained with our method attains much higher sample efficiency. Here are some qualitative results of the agents obtained from different methods at the 2K episode. Our method results in an agent of sufficient social awareness to accomplish the navigation task safely and efficiently, whereas the baseline methods lead to collisions. To conclude, in this work, we propose a learning method, named Social-NCE, to promote robust representations for motion problems. The empirical results demonstrate that our method can consistently improve state-of-the-art methods in various settings. These results suggest that learning from negative data through self-supervision can be a promising alternative to the classical approach for building robust sequential predictive models. For more details, please refer to our paper as well as our code in the following links. Thanks for your attention.